Welcome to the introduction of algebraic complexity. In this module, we will explore the complexity of algebraic computation and decision trees. Algebraic complexity is a field that studies the computational resources required to solve algebraic problems. We will also look at decision trees, which are mathematical models used for analyzing decision-making processes in computation. Let's explore the algebraic computation model. This model provides a mathematical framework for analyzing computational problems involving algebraic operations over structured domains. The basic operations include addition, denoted by the plus symbol, multiplication, denoted by the times symbol, subtraction, denoted by the minus symbol, division, denoted by the division symbol, and comparisons. Now let's delve into decision trees. A decision tree is a computational model that represents algorithms as binary trees, where each internal node performs a test and the leaves contain the outputs. Visually, we have a root test at the top which branches into a left branch and a right branch. Each of these branches leads to leaf nodes, labeled as leaf 1, leaf 2, and leaf 3. Here we introduce the algebraic decision tree model. Key features of this model include that the tests are polynomial equations. The nodes compare expressions to 0, and branching is based on the sign of the result. This model operates over real numbers. For example, a test node may look like this. Is f of x1, x2 through xn greater than or equal to 0? If yes, follow the left subtree. If no, follow the right subtree. Now let's discuss how we measure the complexity in this model. One measure is the tree depth, which is the maximum number of tests performed on any input path. Depth equals the maximum of the path length. Another measure is the polynomial degree, which is the maximum degree of polynomials used in the test nodes. Degree equals the maximum of the degree of f. Now let's understand the lower bounds theory. A fundamental goal is to establish the minimum computational resources required to solve algebraic problems, regardless of the algorithm choice. Key techniques used to find these lower bounds include degree arguments, topological methods, and algebraic geometry. Here are some classical examples of algebraic complexity. The first is the sorting problem, which involves sorting n real numbers using only comparisons between elements. The lower bound for this problem is omega of n log n. The second example is element distinctness, which involves determining if all elements in a set are distinct. The lower bound for this problem is omega of n log n. Let's explore some applications and future directions in this field. Key applications include computational geometry, optimization problems, real algebraic geometry, and machine learning theory. Research frontiers include quantum algebraic complexity, approximate decision trees, parallel computation models, and high-dimensional problems. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.